And hello everybody, welcome back to our next video on the Radiation Learning Journal. And so, in the last video, we talked about when the radiation transport equation can ignore this time-dependent term. And in this video, we want to start including this optical thickness into our radiation transport equation. And that will make it, kind of a more relevant thing. Instead of using S, which is the direction the radiation is traveling towards as kind of the independent variable, we can use this optical thickness, which is like more consistent across the mediums, and it kind of provides a better basis of comparison. So just recap on the terms. Remember that this is the emission term, this is the in-scattering term, and this is the extinction term, which comprises both of absorption and scattering. So beta lambda is the extinction coefficient, as we said before. And what we attempt to do to get rid of S and change the variables to T is the following. We just use a simple chain rule. So we want to use tau lambda as our final kind of a variable, right? So what we need to do is times okay, so this is just a chain rule. Okay, I write it like so. So we need to differentiate tau lambda with respect to S. So tau lambda is just the integral of beta lambda ds. And what then will the variable be after you differentiate it? From the interval, of course, of the interval from 0 to S. And that's where this applies as well. This dids is of course from 0 to S, or wherever S is. So in that interval, since the integral is already so explicitly set for us here, it is integral of beta lambda ds. So the differentiating will just be beta lambda. So that becomes a very simple proposition, simple equation for us. So you'll just have these two in, and I'll just substitute this beta lambda in here, and there you go. That kind of gets rid of all the terms that have S in them. Of course, this thing here you'll kind of have to change all the variables, especially, and I will be in terms of tau now rather than beta lambda. So we'll do tau lambda here instead of S, and that will tell us the optical thickness as well. Okay, so everything you have to use I instead of it being a factor of S, or dependent on S, is dependent now on tau lambda. But for all our intents and purposes, it's more or less the same thing, because it is it's just, in terms of physical meaning, it just means how far the beam has traveled through the medium, right? And now if we use tau lambda, we can actually see how much is being absorbed, or how much the beam weakens or attenuates over time. All right, so that's all we are doing. Okay, so now we just divide throughout by beta lambda. Okay, so I'm just dividing throughout by beta lambda, nothing more. Okay, that's 1. And this is 2. And I'll just cancel this here, and that will be third one. Okay, so remember, the terms still have the same meaning. This is the emission term, This is the in-scattering term, and this is the extinction term. So it is now I want to introduce this new thing, this new quantity, because this is a very important quantity. Sigma lambda over beta lambda, or otherwise known as sigma lambda over beta. Oh wait, no. Sigma lambda plus kappa lambda. Okay, so this is a very special quantity we call albedo. So what's albedo? Albedo is the fraction of when the beam gets weakened, how much of it is due to scattering. So it's the ratio of scattering as compared to let's say scattering and absorption. So that's literally what the math is telling you. How much of the beam weakening, attenuation is the proper word, is due to scattering. Okay, so how scattering-ish is the medium? How much does the medium scatter? How well does the medium scatter as compared to absorb? Okay, so that is what albedo is. Okay, so what is the symbol for albedo? We can take a look at here. Okay, it is this omega symbol, which is in equation 1023. So I'm just doing whatever this page is doing here. Okay, I'm just replacing this, replacing the variables as was said before. So we'll get omega as such. Okay, so maybe I'll do this like that, omega lambda, and I will just get this out on text. Okay, because you don't need another equation, otherwise it takes a lot of memory space. Okay, and then that's albedo for you. So albedo will appear in this part of the equation. Omega lambda. Alright, so what about this term? Well, that's very simple. Okay, so kappa lambda over beta lambda equals to, well, it is just this Alright, kappa lambda over sigma plus kappa lambda. Not an issue. So then what is this then? How can we arrange it such that you have something of a quantity we are familiar with? So I can do this plus omega lambda, sigma minus sigma lambda. So this divided by this is just 1, and what do you know? This divided by this is the albedo. So this is how we convert the terms. So I'll have this 1 minus omega right here, omega lambda, and there we go. We have the radiation transport equation radiation transfer equation in terms of the optical thickness. Okay, so don't get confused. This is still the in-scattering term. This is the extinction term, and this is known as the emission term, right? 1 minus omega lambda. You can't quite see it as obviously as, let's say, this equation, where you can see the kappa and the sigma there. You know what they mean. But now with albedo thrown in, it kind of gets a bit harder to see. but you can still see its emission because you have this black body term here, right? This black body term is strictly dealing with emissions, okay? And this is sort of the emissivity of the system, because okay, so either you kind of absorb or you kind of scatter. So I guess this thing kind of tells you the scattering fraction. So this overall, if scattering and absorption is like a fraction of 1, this will tell you the absorption fraction, right? So that's how you can think of it, right? Scattering and absorption, they add up to 1. What is the fraction that's being absorbed? You get 1 minus the scattering fraction. So this is what albedo is, and this is the in scattering term, this is the extinction term. So that's how we can think of it, right? So you take a look at the textbook. Basically, it's doing the same thing. Instead of lambda, it uses wave number, di d tau n equals to, and this is the extinction term, this is the emission term, and this is the scattering term right there. Okay, so what they go on further to do is they use this thing called the source function, which is basically combines both of these. So which you kind of think of it, it is kind of a source function. So s tau lambda, and we still need s hat to give us like the direction as was used in the textbook, and it is equal to both of these. Why is this called a source function? Because both of these terms actually augment or strengthen the beam, one due to radiation from the medium, emission from the medium, one due to scattering. Alright, so that's what the source function is. So next time you see a big S like this, you know it's the emission term and the in-scattering term combined together. Now, of course, once we substitute that in, we will have a very simple looking equation that looks something like this. Right, and this looks like almost a first order ODE, except that, you know, S is actually more complicated than, say, a first order ODE, right? So in theory, at least in theory, you can have the solution as such using an integrating factor. All right, you use an integrating factor to solve this. Okay, and basically you have this kind of a, I mean, after you integrate, you get this kind of a equation. It isn't too difficult. This is a first order ODE, so you multiply both sides by this integrating factor, exponential tau lambda, and then you integrate. So you integrate this side from 0 to tau lambda, and then you sort of have this expression over here, right? It is basically you kind of multiply, yeah, you integrate in this tau lambda, tau lambda. In this case, it's tau eta because they're using the wave number, and then you multiply or you divide throughout by this exponential tau lambda or tau eta in this case. Then you get this equation. I mean, in theory, you can solve it like that, but of course, the getting actual results using this, it's much harder. So I mean, I'll just leave this here for a reference, cause that's what the textbook does. Yeah. Okay, so this is called the formal solution to the radiative transfer equation. Again, it's nice. It's a nice mathematical statement, but otherwise not very helpful to us to actually solve the thing. So there will be more methods, analytical and numerical methods, that we want to discuss going forward. But this is it. Yeah, basically you have this tau lambda, which is the optical thickness, okay, specific to each wavelength, or in this case specific to each wave number. And okay, yeah, that is all I have. And if you're wondering what this s hat nabla I lambda I eta is, it is the same as dids. Okay, this is kind of not related, but you might see this divergence sign popping up every now and then. So di ds, this is just an extra bit of information, random piece. I know it's a bit annoying. S hat bullet nabla I lambda. So just keep this in mind. Another way to write dids is using this s hat I nabla I lambda. This nabla is just the divergence, and this is the dot product with this nabla sign is the divergence. So remember, this is like if you use Cartesian coordinates, dx partial with respect to x, partial with respect to y, partial with respect to z, and this will be two vectors, okay, as x, as y, as z. So that describes the vectors. All right, the position vector I lambda. Okay, so and I'll use one more. Press enter and I'll get this. Yeah. So you can see how we actually get this, basically through getting the components. Okay. And this is the component vector sx, xy, and sz, xz, and what these are, if you use Cartesian coordinates, they basically boil down to this: sx equals if I'm not wrong, it's yeah, the component is like this. Let's say you have s going in this direction, and this is the x-axis. Sx is just the projection of the vector on the x-axis, which is sx here. So what is this sx, right? Sx equals to s hat times the differential of s with respect to x. Right. So as oh, sorry, I think I got it wrong. Let me redo this. Let's try again. Times, okay, so you want the component of x for this, so we have x dx over ds. All right. Okay, so yeah, so it is like that. But what we must know, of course, is that this is a position vector. This is a vector component of for us, I mean, as we define it, it's a vector component of something, I mean, of a unit vector, right? So this is actually a unitless thing. Excuse me. So the magnitude of this is equals to 1. So all you're left with is just the partial derivative of x with respect to s. So that's how we kind of see things. All right. And if we were to write this out fully using vector calculus, so yeah, this is what we get. So remember, di, you can actually split it up into the x, y, and z components. So here we go. Okay, partial by partial x. Okay, I lambda. Then you times in the dx here, plus partial by partial y. I lambda. Oopsie. I lambda, and have a dy here, and likewise if we consider the z direction, I lambda. Oh, my lambdas are always looking so funny. I lambda dz. Okay, and of course if we divide throughout by s, we will get this. Okay, ds and ds. Okay, so I'm just gonna copy the contents of the bracket and just paste over everything. Alright, so what does this begin to look like? Remember what Sx is, as we are talking about earlier. It is just this 1, and we look at this is Sy 2, and this is Sz 3. And just to avoid confusion, I'll just put this in here, just to make sure you know we are not differentiating the Sx, Sy, or Sz again. And that is what we are left with. Yeah, so we can see that, okay, what this expression here, it is basically what this vector notation is, which is basically what this is here. So hopefully that can kind of convince you that these two are actually just two different ways of expressing the same thing. Okay, so just for you to keep that in mind, you can you know, I don't see us using that a lot, but yeah, the more important thing is, you know, you have this equation with you, and you know what the source term is, physically speaking, and of course, you just introduce what this other way, using the divergence of writing dids. It's just a more complicated way of writing the same thing. Okay, hopefully, I mean, this helps us to bring everything into the Cartesian coordinate system. Maybe it helps it to solve easier later, but it is what it is. Just giving you an insight into what this actually is. Hopefully, it's not confusing you. Yeah. So in the next video, we'll try to talk, get ourselves introduced to solving this radiation transport equation. What do we need to consider? What do we need to think about? And yeah, hopefully we'll work our way towards analytical and numerical solutions. Okay, so thanks for watching. I'll see you guys next time. Bye bye.